In QPSK modulation and its variants, there will be phase discontinuity during the interbit switching time, and this is also true of binary FSK modulation scheme. Now, such phase discontinuity give rise to high level of frequency content in the power spectral density, and consequently this causes interference to the adjacent channels, and this is very much undesirable in communication system. So, today we will study a scheme where we can avoid this phase discontinuity during the interbit switching time, and we will see that this kind of modulation scheme has some kind of memory. So, the modulation scheme which we are going to study today is a modulation scheme which has some kind of memory, and it is a special form of frequency shift keying scheme. So, let us consider a continuous phase frequency shift keying signal as follows. This is over the interval 0 to Tb. We have St is equal to root of 2 Eb by Tb cos 2 pi f1 t plus theta 0, and root 2 Eb by Tb cos 2 pi f2 t plus theta 0. Now, Eb out here is the transmitted signal energy per bit, Tb is the bit duration, and theta naught is the value of the phase at time equal to 0. So, theta naught sums up the past history of the modulation process up to time t equal to 0. So, this theta naught will depend on the past history of the modulation process, and we will transmit this signal for symbol 1 and transmit this signal for symbol 0, and both these signals are defined over the bit interval Tb. Because of this theta naught, we get the phase continuity between the interbit switching time. We will see this as we proceed. So, another way of representing this CPFSK signal is as follows. We can write St is equal to root of twice Eb by Tb cos 2 pi Fct plus theta t. This form is the conventional form of angle modulation, where theta t is the phase of theta. So, when the phase theta is continuous function of time, we find that the signal St itself is continuous at all times, including the interbit switching time. And let us select the theta t as follows. we are considering the first bit interval, that is from 0 to Tb. Okay. Now, this phase theta t increases or decreases linearly with time during the bit interval of Tb second. So, this will be plus when we transmit symbol 1 and this will be minus when we transmit symbol 0. So, let us call this equation 2 and this as equation 3, and we will denote this as equation 1. Let us substitute equation 3 in equation 2 and see what we get. So, if we substitute that, and now if we compare this equation with this equation 1, it is very easy to see that we can write Fc plus h by 2 Tb. We will define h very soon. This is equal to F1 and Fc minus h by 2 Tb, this is equal to F2. So, solving 4 and 5, we will get Fc is equal to half F1 plus F2 and h is equal to Tb into F minus F2. So, this is same as F1 minus F2 upon 1 by Tb. 1 by Tb is your bit rate. So, h is nothing but the normalized frequency difference with respect to bit rate, and this is by definition known as deviation ratio. It is a dimensionless quantity. Let us consider the interval between 0 to Tb and see how the phase varies. So, at t equal to Tb, what I get is plus minus pi h, or Tb minus theta 0 is equal to plus minus pi h. So, this will be equal to plus pi h, which means that the phase will increase for the transmission of symbol 1, and it will be minus pi h, which means that the phase will decrease for the transmission of symbol 0. So, the variation of the phase theta t with time t follows a path consisting of a sequence of straight lines, the slope of which represent frequency changes. So, this becomes very clear from this figure out here. So, this figure depicts possible paths starting from time t equal to 0. So, a plot like this is known as a phase tree. This tree shows the transition of the carrier phase across interval boundaries of the incoming sequence of data bits. Now, from this phase tree, we can observe that the phase of the CP-FSK signal is an odd or even multiple of pi h radians at odd or even multiples of the bit duration Tb respectively. So, for instances like 0, 2 Tb, look here, this is going to be always either it will be 0 or it will be twice pi h, this will be 4 times pi h and that way, whereas at odd instances it will be the odd multiple of pi h. Okay. Now, let us take a special case of h is equal to 1, and this we will see basically will correspond to the case here. If I choose my h is equal to 1, then the difference becomes 1 by Tb. So, this is a special case of FSK which we had studied earlier, and this is known as Sunday's FSK. So, in this case the deviation ratio h is unity. So, according to this figure, the phase change over 1 bit interval we will get is plus minus pi radians, but a change of plus pi radians is exactly the same as a change of minus pi radians modulo 2 pi. So, this implies that in the case of Sunday's FSK there is no memory, that is, knowing which particular change occurred in the previous bit interval provides no help in the current bit interval. So, let us take a case where h is equal to half, and this is the case of interest to us. Now, the phase can take only two values, plus minus pi by 2 at odd multiples of Tb and 0 and pi at even multiples of Tb, and this is very clear from this figure out here, and this figure is known as phase trellis. So, why this is known as trellis is because a trellis is a tree like structure like we had for the phase tree, but with re-emerging branches. So, that is why it is known as trellis. Now, each part from left to right through the trellis of this figure corresponds to a specific binary sequence input. So, let us take one example. So, here this bold lines which have been shown, this correspond to the binary sequence 1 1 0 1 0 0 0, and let us see how do we get this. So, we start with theta 0 equal to 0, and with h is equal to half, we find that the difference between f1 and f2 now is going to be Rb by 2. So, half the bit rate. Here we start. So, when we get 1, we increase by pi by 2, then again we get 1. So, we increase by pi by 2, so it becomes pi, then we get a 0, so it reduces to pi by 2, again it becomes 1, so it goes to pi, and it continues this way. Now, remember that for h equal to half, since the frequency difference turns out to be half the bit rate, this is the minimum frequency spacing that allows the two FSK signals representing symbols 1 and 0 to be coherently orthogonal, in the sense that they do not interfere with each other. We had studied earlier that for two carriers at frequency f1 and f2, for coherently orthogonal case, the minimum frequency difference required is 1 by 2 Tb, whereas for non-coherently orthogonality condition, we require the difference to be 1 by Tb. So, this MSK case is the special case of FSK, where the difference between the two frequencies, that is f1 and f2, is minimum 1 by 2 Tb, and that is why this version of CPFSK, where the deviation ratio is chosen half, is known as minimum shift keying, or also known as fast FSK. Now, let us look at the signal space diagram for this MSK case. Signal space diagram will help us to design the optimum receiver and also help us to calculate the probability of error, and it will also help us in understanding the modulation scheme for MSK. So, we have this ST given in the form 2 EB by TB cos 2 pi FCT plus theta, where theta t is of the form theta 0 plus pi by h. So, in our case we will choose h to be half. So, we will write it as 1 by 2 equal to t. So, this is our MSK. Now, this can be expanded, this ST can be expanded as follows. So, this form can be written as follows. This is a standard form for writing band pass signals. So, we write in terms of the in phase component of cos 2 pi FCT, and SQT forms the quadrature component sin 2 pi FCT. So, here this will become your SIT and this will become your SQT. So, it becomes quadrature modulation with h is equal to half. Our cos theta t we said is of the form let us consider the bit interval 0 to Tb to start with. Remember, plus is for the transmission of symbol 1 and minus is for the transmission of symbol 0. Now, note that your SIT is of the form root 2 EB by TB cos theta t. So, this is a cost function out here. Now, between 0 to TB, theta t at t equal to 0 will have value either 0 or pi depending on the past history, right? And at t equal to TB, the value will go to 0 because theta TB is either going to be plus pi by 2 or minus pi by 2, in which case cos will turn out to be 0. Now, similarly, if we try to evaluate this quantity at theta equal to minus TB, we will find that it goes to 0. So, what it implies that this SIT is some kind of half cosine function with the maximum value at t equal to 0, correct. What we have written here is also valid between minus TB to 0. So, cos theta t, this relationship can be extended between minus TB to plus TB, correct. The only thing is that the algebraic sign is not necessarily the same in both the intervals. Okay. So, if we take that, so the polarity of this cos theta t will depend on theta 0 regardless of the sequence of ones and zeros transmitted before or after t equal to 0. And remember, theta 0 can take only two values, that is 0 and pi. So, your SIT is going to be a half cosine pulse, and let us evaluate that pulse. So, this I can write it as cos of theta 0 plus minus pi 2 TB t, which I can rewrite it as cos theta 0 cos of plus minus pi t by 2 TB, first term I will get. So, and the other term would be minus plus sine of theta 0 multiplied by sine of pi t by 2 TB. Now, remember, theta 0 can take value 0 or pi. So, this quantity will go to 0. So, what we will get from here is my SIT is going to be of the form 2 EB by TB cos theta 0. Cos is an even function. So, this I will get it as cos of pi by 2 TB theta t. Correct? So, depending on what is theta naught, 0 or pi, what I am going to get here is plus minus 2 EB by TB cos of pi t by 2 Tb. So, I will get plus sign when theta naught is equal to 0 and minus sign when theta naught is equal to pi. And remember, this basically SIT is going to be valid over this interval. So, you will have something like this. So, this could be positive or negative. So, this is minus Tb, this is plus Tb, and this is your cos pi t by 2 Tb. So, this is assuming that theta naught is equal to 0. If theta naught is equal to pi, then this will be the inverted. So, polarity will depend on theta naught. Okay. Fine. Now, let us look at the quadrature component, which is your SQT, that is equal to root 2 EB by TB sine of theta t. Now, look here, if you look between 0 to Tb, this value at t equal to 0 will go to 0. At t equal to Tb, it will be maximum. It will be either plus 1 or minus 1, depending what is the value of theta at Tb. If it is plus pi by 2, this will become 1. If it is minus pi by 2, it will become minus 1. And at theta equal to 2 Tb, this will again go to 0. So, what this implies, that it will be a half sine wave between 0 to 2 Tb. The maximum value will be at equal to t equal to Tb, and the polarity of that will depend on sine of theta Tb. Okay? Fine. Now, let us expand sine theta t. So, this I can write as sine of theta 0 plus minus pi t by 2 Tb. Now, we will use this relationship this is Tb, please. So, theta Tb is going to be this. So, what it implies that this is equal to theta 0 plus minus pi by 2. So, what this implies that theta 0 is equal to theta Tb. This should be not plus minus, this should be minus plus pi by 2, correct. So, I am going to use this theta Tb equal to minus plus pi by 2 into this, and let us see what we get. Okay. So, sine theta t, we can write it as follows. In place of theta 0, we write this quantity plus minus pi t 2 Tb. This we expand it, sine of theta Tb minus plus pi by 2 cos of plus minus pi t by 2 Tb plus cos of theta Tb minus plus pi by 2 sine of plus minus pi t by 2 Tb. Now, note that theta Tb minus plus pi by 2 can take values only 0 or pi, because this can take values plus or minus pi by 2. So, what this implies that this quantity when substituted here, this quantity will go to 0. So, we will get our sin theta t to be equal to this quantity, and this quantity if you expand it now, you will get it as, so cos theta b cos pi by 2, that will go to 0. So, you will get plus minus sine of theta t b sine of plus minus pi t by 2 pi p b. So, this being odd function, now if this is simple, we will get it as sin theta t would be equal to sine of theta t b multiplied by sine of pi t by 2 t b, correct. So, your SQT now is going to be either plus 2 e by t b sine of pi t by 2 t b. This will be if theta t b is equal to pi by 2, and this would be equal to minus 2 e b by t b sine pi t by 2 t b if theta t b is equal to minus pi by 2. So, your SQT will be half sine function which will look something like this. So, the polarity of this half sine function will depend on the value of theta t b. So, if this is equal to pi by 2, this will be positive, and if it is minus pi by 2, it will be negative. So, this is your SQT. So, from our discussions, we see that theta 0 and theta t b each can assume two possible values. So, we have theta 0 and theta t b. This could take the value say 0, and this could take value say pi by 2. In this case, the transmission is of symbol 1. Or we could have theta 0 equal to pi and theta t b could be equal to pi by 2, in which case we have transmitted symbol 0. Or we could have this theta not to be pi and theta t b to be equal to minus pi by 2, which is same as 3 pi by 2 modulo 2 pi. This implies that there is a transmission of 1, and theta 0 equal to 0 and this equal to minus pi by 2, it means I have transmitted symbol 0. So, what this means that MSK signal may assume any one of the 4 possible states depending on the value of theta naught and theta t b. Now, based on this study, we will find out the orthonormal basis signals which are needed to represent this MSK signal, and then obtain the optimum receiver and calculates its performance in terms of probability of error. This we will do it next time.